In September 2003, NASA deliberately drove a $1.39 billion spacecraft into Jupiter and let it be destroyed. This wasn't an accident, it wasn't a failure. Galileo had spent nearly 14 years orbiting Jupiter, completed 34 orbits, and transmitted data that permanently changed our understanding of the solar system. And when its mission was over, NASA made a deliberate choice to end it. Not by parking it, not by sending it somewhere else, but by steering it directly into the atmosphere of the most violent planet in the solar system. They did it because of a risk created by Jupiter itself. And that same risk is exactly why, decades later, NASA still hasn't sent anything deeper. In this video, we're going through what we actually know about Jupiter's interior, why going deeper is so difficult, what we found that no one expected, and why one of the biggest questions in planetary science still doesn't have an answer. Before Galileo the orbiter, there was Galileo the probe. In 1995, the spacecraft released a small atmospheric probe that plunged into Jupiter's cloud tops. Scientists had prepared for this for years. They expected a turbulent, water-rich atmosphere, humid and chaotic, consistent with a planet that formed beyond the frost line of the early solar system, where temperatures were cold enough for ice to accumulate. Jupiter should have swept up enormous quantities of water ice as it grew. The atmosphere, the theory said, should be soaked with water vapor. The probe reported something completely different. The atmosphere was dry, not slightly dry, drastically dry. Water vapor readings came in far below predictions. Winds exceeded 600 kilometers per hour and didn't weaken with depth the way models expected, holding speed even 150 kilometers below the cloud tops. The atmosphere was hotter than expected. For years, scientists were genuinely confused. Eventually, an answer emerged. The probe descended into a hotspot. These are rare breaks in Jupiter's cloud deck, where thermal radiation from deep inside the planet escapes upward. Descending air suppresses cloud formation and drives out moisture, making them the driest, calmest regions in an otherwise violent atmosphere. The probe had landed by pure chance in Jupiter's version of the Sahara. It would be like dropping a probe randomly onto Earth, having it land in the Atacama Desert, and concluding the planet has no water. But even as scientists untangled the probe's data, Galileo the orbiter was circling Jupiter and returning something far stranger. Most people think of Jupiter as a big ball of gas. That's not wrong, exactly. But it's incomplete in ways that matter. Jupiter has an atmosphere that doesn't end at a clean boundary. There is no surface, no moment where you cross from outside to inside. As you descend, pressure rises continuously, and the hydrogen around you changes state, from gas to liquid to something with no equivalent anywhere on Earth. At the cloud tops, pressure is about 1 bar, similar to Earth's atmosphere at sea level. Descend to around 1,000 kilometers, and it reaches roughly 200,000 bars. At that pressure, hydrogen stops behaving like a gas or a normal liquid. Electrons are stripped away from atoms. What remains is electrically conductive. It flows, it convects, it behaves like a metal. This is liquid metallic hydrogen, and it makes up somewhere between 75 and 90% of Jupiter's total mass. Temperatures reach around 10,000 degrees Celsius. Pressures are millions of times greater than anything achievable in a laboratory. That churning metallic hydrogen combined with Jupiter's fast rotation, a full day on Jupiter lasts less than 10 hours, generates the most powerful planetary magnetic field in the solar system, about 20,000 times stronger than Earth's. The resulting magnetosphere stretches 7 million kilometers toward the Sun and extends past Saturn's orbit in the other direction. Inside it, charged particles are accelerated to nearly the speed of light. Radiation levels are intense enough to destroy spacecraft electronics in hours. This is what any probe must enter. For decades, scientists assumed Jupiter had a compact, solid core at its center. The reasoning was straightforward. In the core accretion model of planet formation, Jupiter would have started as a rocky seed, a solid body roughly 10 to 20 times the mass of Earth, massive enough to gravitationally capture the gas swirling through the early solar system. The rock came first, then the gas. The core was supposed to be dense, compact, and sitting at the center like a pit inside a peach. When NASA's Juno spacecraft entered Jupiter's orbit on July 4, 2016, its primary mission was to test this model directly. Juno made precise measurements of Jupiter's gravitational field, The idea being that a dense core would create a distinct gravitational signal, visible from orbit if you measured carefully enough. The data came back. The model collapsed. Jupiter's core is not compact. It is diffuse, spread out across as much as half of Jupiter's total radius. Instead of a sharp boundary between the core and the metallic hydrogen surrounding it, there is a gradual transition, dense material blending slowly into lighter material over thousands of kilometers. Scientists called it a fuzzy core. It was not what anyone predicted. Two explanations compete for the answer. One, Jupiter suffered a catastrophic impact early in its history, a collision with a planetary body at least 10 times Earth's mass that shattered the core and mixed it with the gas envelope. Simulations show this is physically possible, but follow-up work found a problem. Heavy elements should settle back down under Jupiter's gravity over time, reforming a compact core. The mixing shouldn't persist for billions of years. It should be temporary. Jupiter's fuzzy core is not temporary. A newer theory suggests the fuzziness formed during Jupiter's growth itself, that the planet accreted material in a chaotic process that never produced a clean core. Supporting this, Saturn also appears to have a fuzzy core. Two planets with the same unusual interior suggests a common cause, not a coincidence. The honest answer is we don't know. The largest planet in our solar system has an interior we cannot explain. The Galileo atmospheric probe lasted 57 minutes. It wasn't the heat that killed it. It wasn't the wind. It was the pressure. When the signal cut out, the probe was 150 kilometers below the cloud tops at about 23 atmospheres. The transmitter was crushed, and it was still in the upper atmosphere, nowhere near the metallic hydrogen zone or the core. To reach depths that could answer real questions about Jupiter's interior, a probe would need to survive pressures exceeding 1 million atmospheres, temperatures of tens of thousands of degrees, and radiation that would shred any known material in minutes. For comparison, the deepest any vehicle has traveled on Earth is about 11 kilometers, to the bottom of the Mariana Trench at around 1,100 atmospheres. That vessel was small, spherical, titanium, and barely instrumented. Jupiter's interior makes the Mariana Trench look shallow. Even if you engineered something that survived, you'd face a communications wall. Radio waves don't penetrate liquid metallic hydrogen. Any signal from deep inside Jupiter would be absorbed by thousands of kilometers of conductive material. The probe would go silent the moment it crossed into the metallic zone. Getting data out would require a relay chain, multiple probes at different depths, passing data upward layer by layer. Nothing like that has ever been built. Then there's the radiation. Galileo was designed from scratch to survive Jupiter's magnetosphere. Radiation shielding, hardened processors, purpose-built components. By the end of its mission, it had absorbed radiation equivalent to roughly 60 million dental X-rays. Its cameras had failed. Multiple instruments had stopped working. The computer was experiencing memory errors. Juno faces the same attrition on a slower schedule. The strongest radiation concentrates in a belt looping around Jupiter's equator, between the planet and its inner moons, where material from Io's constant volcanic activity is ionized and accelerated to near light speed. Any probe descending into Jupiter passes through it. Unshielded electronics fail within minutes. Going deeper is not a matter of funding, it's a matter of physics we haven't solved. By 2003, Galileo was finished. Propellant nearly gone, systems failing, the spacecraft was going to fall into Jupiter eventually. NASA couldn't prevent it. What they could prevent was where it fell. Jupiter has 97 known moons. Most are small, captured rocks, but 4 of them, the Galilean moons discovered by Galileo Galilei in 1610, are worlds of their own: Io, Europa, Ganymede, and Callisto. Io is the most volcanically active body in the solar system. Its surface is continuously reshaped by hundreds of active volcanoes spewing sulfur into space, feeding a ring of ionized gas around Jupiter's equator. Europa is something different entirely. Beneath its cracked, icy surface lies a global ocean of liquid water, kept liquid by tidal heating, the constant gravitational flexing caused by Jupiter's immense gravity. That ocean could be 100 kilometers deep. It could contain more water than all of Earth's oceans combined. And it could, by every criterion we use to define habitability, support life. If Galileo crashed uncontrolled, there was a non-zero chance it would hit Europa, A spacecraft that had been in space for 14 years could carry dormant microbes, bacteria that survived the journey and might survive the impact. If those microbes reached Europa's ocean, we could contaminate the only environment in the outer solar system that might already harbor life. We would never be able to determine whether anything we later found there was native or whether we put it there ourselves. NASA chose to eliminate the risk entirely. They steered Galileo into Jupiter's atmosphere and destroyed it. This principle governs every future mission. Any spacecraft heading toward Jupiter or any other world with potential for life must be sterilized to strict protocols or designed to be destroyed before it can pose a contamination threat. This adds layers of complexity and cost to mission planning that have no direct scientific return but cannot be skipped. In 2017, Juno flew directly over the Great Red Spot. The storm has been observed from Earth for more than 350 years. It is wider than the entire planet Earth. Juno's microwave instruments revealed it extends more than 350 kilometers deep, far deeper than anyone expected, reaching into regions where the atmosphere should be too hot and pressurized for a surface storm to hold together. How it anchors itself that deep is not understood. The Great Red Spot is also shrinking. In the 1800s, it stretched roughly 41,000 kilometers across. Today, it measures about 16,500 kilometers, losing close to 1,000 kilometers of width per year. Some models say it will stabilize. Others say it may vanish within decades. No model adequately explains why it's shrinking. Juno also found something unexpected at Jupiter's poles: 9 massive cyclones at the North Pole, each larger than the continental United States, locked in a stable octagonal arrangement around a central storm. 5 at the South Pole forming a pentagon, wind speeds exceeding 300 kilometers per hour, stable for years, not merging, not drifting. No computer model can replicate these patterns. The physics that produce and maintain geometric storm arrangements on a rotating gas giant are not currently understood. We can see the structures. We can measure the winds. We cannot explain what we're looking at. NASA and ESA are not walking away from Jupiter. The European Space Agency's JUICE, Jupiter Icy Moons Explorer, launched in April 2023 and is en route, scheduled to arrive in 2031. Its focus is Ganymede, Callisto, and Europa, examining their potential for habitability and the structure of their subsurface oceans. NASA's Europa Clipper launched in October 2024. It will reach Jupiter in 2030 and conduct dozens of close flybys of Europa, studying the ice shell's composition, any material erupting from the surface, and the depth and chemistry of the ocean beneath. It is arguably the most consequential planetary science mission currently in flight. Neither mission goes into Jupiter, both orbit and observe. The atmosphere, the metallic hydrogen interior, the fuzzy core, those remain beyond the reach of anything currently built. But the engineering conversations are ongoing. Nuclear-powered probes that generate their own electricity independent of sunlight. Swarms of small probes descending to different depths simultaneously. New radiation-hardened materials. Better thermal protection designs. None of it is hardware yet. But the direction is clear. The question of what's inside Jupiter isn't one anyone is willing to leave unanswered forever. Why won't NASA go deeper into Jupiter? The honest answer isn't fear, it's physics. The pressure will crush any vessel we know how to build. The radiation destroys electronics before meaningful data can be gathered. The heat at depth exceeds anything our materials can withstand. And even if a probe survived all of that, the electrically conductive metallic hydrogen surrounding it would absorb every signal it tried to transmit. Beyond the engineering is the ethics. Europa may harbor life. Any mission to Jupiter carries contamination risk. That demands caution in how missions are designed, deployed, and ended. But here's what doesn't get said enough. Jupiter was the first planet to form. Its gravity shaped the orbits of everything that came after. It cleared debris from the inner solar system that might otherwise have made Earth uninhabitable. Jupiter's existence is part of why Earth is the way it is. Understanding it, from the cloud tops all the way to the fuzzy core, means understanding the conditions that produced a solar system capable of supporting life. We don't know how that core formed. We don't know what anchors the Great Red Spot 350 kilometers deep. We don't know what organizes cyclones into perfect geometric patterns at the poles. We don't know how deep the winds reach, what drives the metallic hydrogen's convection, or what the very center of the planet looks like. Every mission has answered questions. Every answer has produced new ones. Jupiter protects its deepest secrets behind layers of pressure, heat, and radiation that our technology hasn't caught up to yet. Someday it will. For now, we orbit. We measure gravity from a distance. We watch the storms from above. We send our spacecraft as close as they can survive, and we listen to everything they say before Jupiter silences them. It is slow work. It is expensive work. And it is necessary because Jupiter, massive and strange and 4.5 billion years old, is one of the most MP.